Vector space. By definition, a non-empty set V is said to be a vector space over a field capital F if claim 1 V comma plus is an abelian group. Claim 2 for every alpha belongs to F and small v belongs to capital V, there is an element alpha into V belongs to capital V such that first condition alpha into u plus V equal to alpha u plus alpha V. Second condition alpha plus beta into u equal to alpha u plus beta u. Third condition alpha into beta u equal to alpha beta into u. Fourth condition 1 into u equal to u. For all alpha beta belongs to F and u comma V belongs to capital V. Now first problem, show that R cross R is a vector space over R under the addition and scalar multiplication defined by A comma B plus C comma D equal to A plus C comma B plus D and alpha into A comma B equal to alpha A comma alpha B. So by this addition and scalar multiplication, we need to prove this vector space R cross R is a vector space over the field R. So here R cross R is our vector space V and this R is our field capital F. Okay, so now as per claim 1, we need to prove R cross R comma plus is an abelian group. So with respect to this addition, we need to prove this is an abelian group. R cross R is an abelian group. Abelian group means we need to prove 5 conditions. First one is closed, next associative, then existence of identity element and existence of inverse, and at last commutative. So if we prove these 5 conditions, then we say it is an abelian group. So first we check for closed. So closed means we need to consider any 2 elements of R cross R. In R cross R, all the elements will be in the ordered pair form. So A comma B in this shape. All the elements in R cross R will be in this shape. Okay, R cross R. It will be ordered pair. So if we choose any 2 elements like 1 comma 2 and with respect to addition we need to check plus 3 comma 5. So we have these elements 1, 2, 3, 5 are real numbers. So we can choose like this. So if we add these 2 numbers, what we get? 1 plus 3 is 4 and 2 plus 5 is 7. So another point. Here also 4 and 7 are real numbers. Therefore, this is also in the ordered pair form and it belongs to R cross R. So we can say yes, it is closed. Similarly, associative. If you add another number 0 comma 5 with this combination, that is this add, we add these 2 and with this if you add 0 comma 5, so this sum is 4 comma 7. So we'll be getting 0 plus 4 which is 4 comma 5 plus 7 is 12. So if we add these 2, suppose we add these 2 first, that is 0 comma 5 and 1 comma 2 first, we get 0 comma 5 plus 1, 0 plus 1, that is 1 comma 5 plus 2 is 2. Sorry. 0 plus 1 is 1 and 5 plus 2 7. So we get 1 comma 7 plus 3 comma 5. So if we add with this 1 comma 7 and 3 comma 5, we get 4 comma 12, the same answer. So it is associative. Okay, so closed proved, associative proved. Similarly, commutative also we can easily check. That is adding 0 comma 5 plus 4 comma 7 is equal to 4 comma 7 plus 0 comma 5. So commutative also true. So here we can say clearly R cross R is closed, associative and commutative. This we can say in general. Commutative and commutative with respect to the addition defined. Commutative with respect to the addition defined in this problem under plus. This is the binary operation defined here. So these three properties are true. Now we need to get the additive identity. So additive identity element in R cross R. In R cross R is, what is R cross R additive identity element? Normally in real numbers additive identity is 0. So in R cross R it should be an ordered pair. So we get 0 comma 0 as the additive identity. Okay, and similarly additive inverse of any element of R cross R. Additive inverse of any element, we can choose any element, say x1 comma x2 from R cross R, and we can say get the inverse of this element, which is the negative of the x1 and x2. So that is minus x1 comma minus x2. So we get this identity element as well as the inverse element. Identity element is only one for the whole R cross R. But for every element of R cross R, there exists an inverse in the same R cross R itself. So for x1, x2, the inverse is minus x1 comma minus x2. Thus, the 5 conditions are satisfied. All the 5 conditions are satisfied. Therefore, we can say, yes, this R cross R is an abelian group under plus. So, simply saying R cross R, comma, plus is an abelian group, since it satisfies the 5 condition. Closure, associative, commutative, and additive in, identity exists, additive inverse exists. So commutative abelian group. Okay, now we need to go for climb 2. As per definition, defined in this problem, they have defined a comma b, the addition as a comma b plus c comma d equal to a plus c comma b plus d, and the scalar multiplication like this, alpha into a plus a comma b equal to alpha a in comma alpha b. So considering this definition, we go for getting the 4 conditions proved. Okay, so for that let us consider alpha comma beta belongs to, here our field is R. Okay, so we choose alpha comma beta belongs to R. R means real numbers. And let us consider U as x1 comma x2 and V as y1 comma y2. Both belongs to the set R cross R. So this is what we need to prove. This R cross R is a vector space under R. So now we choose 2 elements from the field and 2 elements from the vector R cross R. Okay. Now we try to prove the first condition, that is A. We need to prove alpha into u plus v equal to alpha u plus alpha v. Okay. So alpha u plus alpha v means, now let us consider the left hand side. The left hand side is alpha into u plus v. Now substitute this u and v. We get alpha into, instead of u we put this value x1 comma x2, the ordered pair x1 comma x2 plus v is y1 comma y2, ordered pair y1 comma y2. Now we add these two elements first, then we apply the scalar multiplication. So alpha into, when we add, we get the first element as x1 plus y1 as per definition. x1 plus y1, we need to add the corresponding elements here, comma, the next x2 plus y2. Okay, now we make a scalar multiplication. That means we multiply this alpha inside. So we get the ordered pair alpha into x1 plus y1 comma alpha into x2 plus y2. So let us keep this as equation 1. Now we do for the second, that is the right side of the part, which we need to prove. We bring these two, the left hand side as well as the right hand side are same. Now consider the right hand side. Which is our right hand side of this first condition? The right hand side is, see here, this one, alpha u plus alpha v. So consider alpha u plus alpha v. So which is equal to alpha into, for u we substitute x1 comma x2 plus alpha into, for v we substitute y1 comma y2. Okay. Now here we make the scalar multiplication first for each term, then we add. So if we apply the scalar multiplication, we get alpha into x1 comma alpha into x2. This is the first term, plus here also make the scalar multiplication. So alpha into y1 comma alpha into y2. Now we can add these 2 points. So adding first elements, we get alpha x1 plus alpha y1. The next ordinate is alpha x2 plus alpha y2. Okay, now we can take alpha common within. So alpha into, we get x1 plus y1 comma alpha into x2 plus y2. Okay, now look back. That is our first left hand side result is also alpha into x1 plus y1 comma alpha into x2 plus y2, and now we are getting the right hand side answer also the same. So we consider this as equation 2. Therefore, from 1 and 2, equation 1 and 2, it is true that the first condition alpha into u plus v equal to alpha u plus alpha v. Okay. Now we move to prove the second condition. What is our second condition as per the definition? Second condition as per definition is alpha plus beta into u equal to alpha u plus beta u. So we prove alpha into alpha plus beta, two scalars. Alpha plus beta into u equal to alpha u plus beta u. We need to prove that. Again consider the left hand side. As we did before, we consider the left hand side, which is alpha plus beta into u. So substitute for u, or u is x1 comma x2. So instead of u, we put x1 comma x2. Now I consider this alpha plus beta as a single scalar, and I operate this alpha plus beta with x1 and x2. Okay, the scalar multiplication. So how I write means, I keep this alpha plus beta together, alpha plus beta into x1 comma alpha plus beta into x2. Okay, now let us keep this as it is. Let's try for the right hand side how it comes. Let's see. And when both the cases goes equal, we can stop there. Okay, so see here. Consider the right hand side. What is the right hand side? Alpha u plus beta u. Okay, so alpha u means alpha into x1 comma x2 plus beta into x1 comma x2. Okay, now again make a scalar multiplication in each term. We multiply this alpha with x1 and x2. So we get alpha x1 comma alpha x2. Similarly, we multiply this beta with this x1, x2. So we get beta x1 plus beta x2. Okay, now we add. When we add the first elements, it is alpha x1 plus beta x1, comma second elements alpha x2 plus beta x2. Now we can take this x1 as common, no? So from this alpha x1 plus beta x1, we can take x1 common, so that we get alpha plus beta into x1, comma here also we can take x2 common, so alpha plus beta into x2. Okay, so we are getting both the hands same. So we can consider this as the left hand side result as equation 3 and the right hand side result as equation 4. So from equation 3 and 4, therefore from 3 and 4, the result is true. That is the second condition is true. 3 and 4. We can say alpha plus beta into u equal to alpha u plus beta u. Okay, now we proved this two conditions. Next condition is C, that is to prove this third condition as per definition. third condition is alpha into beta u equal to alpha beta into u. So we consider that alpha into beta u equal to alpha beta into u. Here I consider left hand side first. Our left hand side is alpha into beta u. What is our u? x1 comma x2. So I substitute for x1 comma x2 for u. Beta into, for u I substitute the point x1 comma x2. Now I apply this beta scalar multiplication within the bracket. So I get alpha into the ordered pair beta x1 comma beta x2. Okay. Now again I multiply this alpha with the elements. So I get alpha into, I'm multiplying alpha with this beta x1. So I make bracket here beta x1. Alpha into beta x1 comma alpha into beta x2. But you know, these alpha, beta, x1, x2 are all real numbers. Since alpha, beta, x1 and x2 are all real numbers, and we know R with respect to multiplication in real numbers it is associative. That is, we can say R comma dot, that is normal multiplication, R comma dot is associative. That is always an abelian group, so it is associative. Okay, so here we can associate, so that I can change this bracket as within the elements, that is alpha into beta x1. I can write this as alpha beta into x1 comma, here also I can associate alpha beta into x2. So see, now I can take alpha beta outside. When I take alpha beta outside, the remaining is x1 comma x2. What is x1 comma x2? That is u. So alpha beta into u. Now I am getting the right hand side directly. Alpha beta into u, which is our right hand side. Therefore, we can say the result is true. That is the third condition. Therefore, alpha into beta u equal to alpha beta into u. This is true. Now we need to prove the third condition. So what is our fourth condition? We have proved three conditions. What is our fourth condition? As per definition, 1 into u equal to u. So we need to prove that one. So the fourth condition is to prove 1 into u equal to u. So now consider the left hand side, which is 1 into u. What is u? 1 into u is x1 comma x2, which is equal to, now apply scalar multiplication here. So we get 1 into x1 comma 1 into x2. We know in real numbers the multiplicative identity is 1. So 1 into x1 is always x1. Similarly, 1 into x2 is also x2. Therefore, we are getting x1 comma x2. What is x1 comma x2? Which is u. So we got the right hand side. We started with 1 into u. that leads to the right hand side, U. Therefore, we can say this property is true. Therefore, 1 into U is equal to U. So, altogether, we can say, since it satisfies both the claims, R cross R is a vector space under the defined addition and scalar multiplication. Under defined, as per the problem, defined addition and scalar multiplication. Scalar multiplication. So this is proved. So we need to prove the two claims as per the definition of vector space. Hence proved.